Oh, hi guys. Yeah, welcome to the AI Kickoff. We're super glad that you're here. And yeah, just to kick things off right now, we have workshops.
Oh, me. This nothing. Okay, there we go. Which one do I click on?
This one.
Okay. Why is it like this? Hi. Howdy, y'all. I'm Jackson. I am the workshops director. Can we get some applause, please? Woo! Yeah. So, as you may have a little inkling, we're doing things a little bit differently this quarter, especially in workshops. Now, in past quarters, we've had beginner track and advanced track, segregated based off of skill level. We believe that there was some room for improvement with the model, let's say. So now we still have two tracks, but they are different. They're concurrent, or you can do them sequentially, but like they're designed in such a way where, in theory, the two tracks are completely independent, and you can go to whichever one interests you. We have applied track, which is going to be Wednesdays at this time in this room. That's probably going to be the one that's more people are going to want to go to. And then there's theory track, which is going to be Mondays 6 to 8 in Kaplan at A65. And then, we're changing it up. Before we said completion of advanced track is necessary to join projects track. Now, a completion of applied track is what's mandatory, and theory track is heavily recommended, but not mandatory. And also, because this is experimental, not gonna lie, could be subject to change. Also depends on who the new directors are. So applied track, right? So who is this for? So this is for what I'm guessing is a large chunk of you guys who, are like these math nerds up here. Like, I don't want to hear anything about this linear algebra. Get out of here. I just want to, learn the bare minimum of math that I have to make a cool AI, right? So this is going to be teaching you the practical side of things, just the bare bones knowledge that you need in order to, write the code and make the cool projects. And what do we do exactly in applied track? Well, we have a set of 4 notebooks, which are, well, for those of you who don't know what a notebook is, it's basically, like a big thing that you can run on your computer and you go through and you fill out, boxes. It's self-explanatory. You'll see.
Good for ML.
Yes, good for ML. Very good for ML. Specifically, we're going to have 4 self-paced notebooks that we can all work through. And by the end, you're going to have of your own ML models from most of these notebooks. And these 4 notebooks are catered to different skill levels. So we have one notebook for if this is your first time ever hearing about anything about programming and you want to learn, what the heck this Python thing is. Oh, we have another slide. What this Python thing is, that's the intro to Python notebook. Now, if you have a little bit of Python and programming experience, but you're like, I don't know what the hell a neural network is. That's what our second notebook is, which is going to be neural networks with MNIST, which is a data set of handwritten digits. And so, this is going to get you set up and teach you what exactly this PyTorch thing is that you might hear people gabbing on about. After that, we have CNNs with Sci-Far 10. Those words may or may not mean anything to you. But this is for people who, have done like the MNIST notebook, have a little bit of neural network knowledge, but really want to begin, actually experiencing PyTorch to its fullest. And then finally, so that is the absolute minimum for projects. And then highly, highly, highly recommended for projects is the very last notebook, which is also the hardest one, which is RNNs for text classification. And so this is for those of you guys who have, a pretty good idea of, what this whole PyTorch thing is about. But you're like, what can I do with it other than classify things? Let's do something a little bit cooler, right? Well, I mean, you're still classifying things, but differently. Yeah, you'll see. So, and then next up, we have theory track, right? So who is this for? Well, you want to know exactly how and why these neural networks we're talking about work. If you're doing applied track, you're probably going to see a lot of lost stop backwards. What the hell does that mean? Do you want to get a glimpse into what the cutting edge problems and tasks that ML scientists are working on today? This is for you in theory track. This is also going to be meeting weekly, again, on Mondays instead of Wednesdays. And this is going to give you a foundational understanding of ML and deep learning while peering at the math behind the curtains with really little to no programming. So, if you're showing up here, you're really not going to be writing much code. You're instead going to be getting a really good hands-on understanding of how all of these neural networks are working. And so we have a little bit of a tentative roadmap up here. So again, we're doing things a little bit differently this quarter. It may or may not end up being exactly this roadmap. But we're planning on week 3 being an introduction to gradient descent neural networks, week 4 being convolutional neural networks. Week 5, we're going to go over embeddings, RNNs, and LSTMs. And well, there's 3 more weeks, but you guys can read that. And I'm guessing for a lot of you, those words might be, a word soup for you right now. That's okay. That's what Theory Track is for. We're going to get you up to speed on all of these. It's going to be very cool. Sort of like reading group vibes if you've ever been to one of those.
And the best thing about Theory Track is even if you're in projects and you just want to be like, hey, this week's topic seems interesting. I've never done it before. And if your group members are okay with it, feel free to just like, join in at one of the sessions when say we're talking about, online learning ensembles and epsilon delta privacy. Like that's something we have never talked about before in workshops. But now we're able to talk about it because of, the fact that we have 2 separate tracks that are running concurrently now. So if you're in projects, you're still more than welcome to come to a lot of these meetings if you just want to get a better understanding of a lot of the topics that you may be working with yourself in the future.
And that's also a very good segue to one final point that I had, which is for both of these tracks, we do encourage you to, attend every single week, but they are designed with a little bit more flexibility in mind than before. So, if you have any experience with any of our previous offerings for workshops, you might know that it's, a little inflexible and week by week, sort of building upon itself. Now, there still is some building upon itself, but hopefully if, you have to, miss a week or 2 because you're going on vacation or whatever, that will be a-okay. Also, if you have any suggestions, this is just a tentative list. If you have any suggestions of any cool topics that you want to hear us talk about, please, let us know. And now I'm going to hand it over to Pratik and projects.
All right. So once you're done with the workshops, projects is all about building your own deep learning models from scratch. So the gist of it is you're going to get together in groups of 3 to 4 people, and you're going to work on some sort of a text or image generation project or some sort of Kaggle competition. And we're going to guide you along the way. We're going to do onboarding. We're going to teach you the basics of PyTorch and building these models. And we're mostly going to help you with debugging and model support throughout the quarter. But most of the work is going to be done by you. And at the end of the day, you're actually going to be building the models yourself. So brief schedule of how it works. So today we're going to go over some logistics and introduce all of our projects. And we're going to fill up our forms to put all of you in teams. We're going to match you roughly based on your skill level. And also you can decide what project you want to finally be in based on the presentations that we're going to show you in a second. And yeah, we're also going to give the notebook about introducing you to PyTorch. If you've already been in projects before or you're very familiar with PyTorch, then you can feel free to just skip that and start working straight on the skeleton code or in the competition. Or you can ask any of the officers here if you want help setting up like Git, Conda, VS Code, any of that stuff. So that you'll be ready for Monday, which is when we'll finally meet your teams and get started working on your projects. So projects are roughly about 3 hours per week. We have 2 meetings on Monday and Wednesday from 6 to 7:30. The image and text generation are going to be at the ACM Clubhouse. If you're doing the Kaggle competition, then look in the Discord for where the locations are going to be. This quarter, we got way more applications than we can actually accommodate in our room. So the Kaggle competition location may be changing a little bit from week to week. So do keep an eye out on the Discord. And yeah, if for any reason you can't make a meeting, then try to let us know. And more importantly, try to let your team know. Yeah. So the projects ends in what's called the AI Cyber Symposium, where basically everyone from ACM AI projects and ACM Cyber projects presents what they worked on during the quarter. And yeah, the best generative model results in both text and images will get added to the Discord server as emojis or bots respectively. So yeah, you can sort of immortalize your project in like ACM history. So this quarter's projects, we're doing our brand new text generation track where we have 2 options, approaching it from more old school RNN perspective, which is better if you're newer to PyTorch, or using a newer GPT model, which we can now finally do thanks to our new server that we just got last quarter. And yeah, we also have image generation, which we can approach through GANs or diffusion. And lastly, we have a Kaggle competition, where it's a competition by Google on the platform Kaggle, where we're basically trying to figure out from smartphone sensor information what a person's exact location is. So now some officers are going to tell you a bit more about each of these projects, starting with GANs.
Okay, so our first track we're offering this quarter is the GAN track, which is a relatively new track we developed this last summer. The gist of it is basically you're going to get a large data set of existing emojis from different platforms like Facebook, Apple, Google, and then you're going to try to generate your own emojis. They will probably come out cursed like this one on the slide, but it will hopefully be fun. And then once you like get your emojis, you can like take them and like use them in your like Discord servers or anywhere else. So that's also fun. Next track.
Awesome. So I'm here to introduce the Kaggle track, and for this quarter, our Kaggle competition will be the Google Decimeter Challenge, which will be really, really cool because you'll get to be working with GPS data, time series data, and you'll be able to apply a lot of the learnings you'll have learned inside the Transformers or RNN track here. So what exactly do we do in the Kaggle competition track? We're currently running track, which means that we're going to have the Kaggle track every quarter, and you can always come back to it. So it's not exactly like the other projects track where we'll be repeating the same content. We'll have new content every quarter. So, what exactly is the Decimeter Challenge? Well, I'll tell you why this is really cool and why you should join it. So your phone geolocation is what your phone does, what the GPS in your phone does. The issue is that your phone GPS is not very good. It's only accurate to the meter. And while that's pretty good for modern phones, it's not good enough for some of the applications we'd really like. So what we want to do in this challenge is we want to improve GPS accuracy to the decimeter or centimeter with ML. And some applications of this is carpool detection. So like if you have very accurate GPS, you can detect when many people are in the same car. So it'll help like Google Maps like calculate congestion better. You can better self-driving. So self-driving cars can better locate themselves with just pure GPS. And we can even do AR because we can locate where people are exactly and then like spawn virtual objects in their view. And yeah, so CAD competitions will be largely self-guided with mentorship from officers, so me and Leo. So onto the technical side, why join? Well, you'll get to train models on nanosecond accurate time series data from GPS satellites, accelerometers, and magnetometers. You'll get to apply like learnings from transformers or any other kind of recurrent network, which will be good for this kind of task. One actually really interesting part is you'll have to account for special relativity, or you could just feed the data into the model and just hope the model learns how to account for that. There's also a really large prize pool. So if we all do very well, we can win the entire $15,000 prize pool, which we can use to buy a ludicrous amount of GPUs. And also our data is very clean. So like the ground truth is very good. It doesn't have like some of the problems that come with other CAD competitions where there's like mislabeling and stuff in the ground truth. And the baseline is very simple. So to get like a decent performance, it's not too hard, but your model will probably look like that. And there's a lot of ways you can improve your model to get it really down to like decimeter or centimeter level.
All right. Hi, everyone. I'm Gregor. I'm going to be introducing text generation. Really, throughout this project, we're going to generate text using either old school RNNs or more recently developed transformers. We're going to be focusing on using the tiny Shakespeare dataset, which is essentially a collection of all of Shakespeare's writing. And we're going to train our models on that and have it generate our own Shakespeare. The quality may vary. However, we think it'd be a really interesting project. It'll be loads of fun to learn. And just really quickly, we're going to go over a little bit about RNNs and the differences between them and transformers. So these slides are from another presentation on recurrent neural networks. Basically, what a recurrent neural network is doing is it's a set of neural networks acting on a sequence of inputs, and it's generating the next token. So the next token is either the next word, the next character, or some other level of encoding that you get to decide. Note that this is not necessarily the same size as your input. So especially with models like ChatGPT, they essentially take a different kind of model, a transformer, to generate an entire output sequence. The key note and key difference between RNNs and transformers is that in RNNs, we have something called a hidden state that typically gets passed through each different layer of the network. However, that hidden state is limited in size and can't really contain all the information we'd like to know about a sequence. So what transformers do instead is they use a mechanism called attention to look at an entire sequence at once and encode those values into the training data.
So I should have just posted the team formation form on Discord. So if you're part of projects, then go check that out right now. And onto that, based on what your results are in the form, we'll put you together in the team on Monday. And yeah, so that's about it for now. I'll give you all a minute. If you just confirmed your projects thing, then you probably won't have been added to the server just yet. So I'll do it by tonight. And if for some reason you're still unable to access it by tomorrow, then DM me and I'll look into it. But yeah. So I'll give you all a minute and then we can move on to the reading group.
It's our team, the AI Lobster. Give it up for him. Woo!
Hello all, I'm Artine. So this is so this is reading group. We do this. Okay, let's go to it. Yeah, I'm gonna be doing the first one this weekend, Saturday, 12 to 2. Reading group is kind of just like an opportunity to get beyond just like the basic ML stuff. If you want to look at like new research topics or pretty much just beyond the basics of machine learning. So the first one is going to be me this Saturday. It's going to be on quantization, LoRa, and why attention is a lie the government has been telling you all along. Pretty much, it's going to be about how we can compress models, how we can train them faster and better on our personal computers. And then the last one is recent papers and things that have been talking about this, the self-attention mechanism in transformers and the role it plays. So if you guys want to, if those interest you, those topics interest you, come this Saturday. Next. Okay, yeah, week 3, we're actually going to get generative video models. So this is like text to video generation. We already have, you know, text to images. If you've seen like DALL-E or any of those AI art makers, but this is going to be a guy who actually works at Stability. So this is like, he knows his stuff, and he's going to talk about diffusion models, how they work, how you can actually get not text to images, but text to actually creating videos and how they're working on that, and also future works of how that's going to develop.
Yeah, like this is one of the co-authors of the stable video diffusion paper. If you guys have heard of stable diffusion, you know, text to image, AIR, or whatever, it's the first model that first text to image model that became open source. And they recently, like a month ago, released a video version of the model, and he is actually one of the co-authors on that paper. So this is going to be very exciting.
So then, yeah, after that, we're going to have week 5, we're going to have a deep dive into transformer mechanistic interpretability. Wow. That's interesting. I think that's going to be about probably trying to understand how the model's learning and what's happening there. Week 7 or week 6, that's me again. It's going to be on neural radiance fields and Gaussian splatting. So this is like a cool technique where you can actually like just take videos of a place and then you can recreate a photorealistic like scene of it with machine learning, right? Before you have techniques like 3D scanning and stuff, but those don't get super photorealistic. This is going to be really cool, and there's like a lot of papers and a lot of interesting things, and it'll kind of be like, what? That's real? It is. And then week 8, we're going to have some statistical physics to neural computation. Wow. The underlying geometry why intelligent systems work. Yeah, what is, I don't, that's going to be a topic.
It's neuro AI. It's a topic that one of our officers, Kevin, specializes in, and he has done. He's been a visiting scholar at the Science Foundation. He's done a lot of work on neuro AI in the past. So it's going to be very interesting to see. You know, like when we think of machine learning, we're like, oh, it's deep learning. It's a bunch of layers. You know, we're looking at all these things, but you know, there are real applications of machine learning to understand neuroscience and using machine learning to model how our brains work, and that's what he's going to be talking about. And yeah. Then we have some quick announcements / previews of events for the quarter.
Yeah, so just some things to keep an eye out. Our first event is going to be a collaboration with Bruin Linguistics. So if you are a Ling and CS major or somebody that's interested in like NLP or just want to like check out like a cool field in AI, we have a very chilled coffee chat with 2 professors here at UCLA. And what's really nice about this is that this is more of like a smaller setting. So you actually get the chance to interact with these professors and ask your questions to them like one-on-one, and you just really get to have like a conversation and to spend time with them. And yeah, so currently we are aiming for either January 24th or 25th. Still trying to figure out the schedules with the professors, but we will let you know as soon as possible. So keep an eye out for this event. It's going to be really fun.
Who's the major here? Can I see a hand? Okay, we have a few. Yeah, pretty good. This is going to be the event for you because it is looking at how, you know, computational linguistics and a lot of sense what we call, you know, natural language processing and the machine learning side come together and how they may be different and similar. And this is going to be a really great event for that.
Yeah, and you never know. These might be your future professors one day. So great chance to get to know them. And our next event that we have for this quarter so far is in week 4, and this is going to be a seminar with Dr. Alyssa Adams. And what the purpose of this event is just to give you guys a glimpse of all of the possible applications that AI has, as well as like different career opportunities that you guys may have in the future. And so she is a research scientist and a postdoc fellow, and she specializes mostly in computational biology with AI. And so, yeah, this is just a great chance for you to ask her any questions you might have about this like field of AI, and as well as talk about like AI ethics. And the nice part is that it's on Zoom, so you really don't have to go anywhere, and you can just do it like from your dorm in your PJs. So definitely keep an eye out for this event. And some other things to also just look forward to. We're gonna have a couple AI socials, and we just want to get to know all of you and just have a chance for you guys to interact with all of us. And so we have an AI hike that we're planning on week 3 to 4 because that's been really popular lately. And then we're going to maybe have like some post-project socials such as boba runs, maybe like late night in and out runs. So yeah, be sure to come to the meetings because you never know when it's going to happen. And finally, we just have a couple announcements from Outreach. We do have a podcast coming out soon, so keep an eye out for that. And we are still teaching our classes. And yeah, that's pretty much everything that we have for this quarter. Keep in touch with us. Here's our Discord as well as our link tree. And
yeah, so again, that's the attendance code if you do that for the UCI members portal. So can I have a see of hands? Who's here for workshops? Okay, we have a decent number of people for workshops. Who's here for projects? Okay, so projects people, let's go to near the back. So coming near the back, Pretty's gonna be there with you. I'm gonna announce the first steps and go through the projects in more detail. And for workshops, just come to the front. We're gonna do kind of group divisions for depending on your skill level in a little bit. So
5-minute break.
yeah, let's have a quick 5-minute break while all of y'all do that.
Right. So game plan you basically gonna have to provide basically skill level. Sorry. Probably get like laid back. It's not solid yet. Like it's gonna be very few. I don't think we have yet, so but if they are, come find me, I'll figure it out. So you can help. Wait, I can't work.
The guy
Daniel. I met him. Yes.
That's
Yeah.
I'm so hyped.
All right. All right. You guys want to?
You don't have to keep wearing the lobster if you don't want to, but
I think it's who I am.
Are you?
Yeah.
Wait.
What the
Are you going to post it on Instagram?
Oh, yeah.
Okay, slay. We need pictures. We need more pictures.
Yes.
I have some videos.
Yeah. Nice.
Have fun. Okay, are you staying?
Yeah.
Okay, cool. Have a meeting. I'm gonna head over too. But take pictures.
Okay. Wait, where are you heading?
I have to go to a meeting at 7.
Oh, okay. That's fair.
Yeah.
All right, have fun.
All right. You guys can hold down the fort. I'm gonna go find a pigeon.
All right. Progress people, still keep doing your thing in the back. Workshops, let's get closer to the front because we're going to be talking about things that we don't want to distract progress people, so I don't have to scream. Okay. The way that workshops is kind of going to work in the future is the first little bit of time, like 10-ish minutes, we're going to be kind of going through a concept that is going to be directly relevant to the notebooks that you guys are working on. Specifically, it is going to be basically a very short version of theory track and a very quick overview of what these are. Because some of y'all may come in without any machine knowledge and want to not have to force you to attend every single theory track. If not necessary, though, that would be very, very helpful. So before we get to that today, we actually wanted to see like a show of hands of like in terms of the sort of level that you are at, and to kind of give you a little bit more insight into what these 4 notebooks are. As we said, the Intro to Python notebook is for people who have like basically never done programming before, and it's a pretty simple and quick notebook that you learn how to do, operations in Python, what libraries mean, addition, subtraction, stuff like that, right? It's a quick introduction to that. MNIST, a neural network with MNIST is great for people who came from beginner track or people who have already Python knowledge. That is a good place to start. And a CNS with SciPy is also great for people who came from beginner track. It just depends on where you're, how comfortable you are with, starting with PyTorch. Like, if you came from beginner track and you think the beginner track notebooks are easy or like they're easy to understand, like you think you really understand, what it's like to code with machine learning libraries now, it is fine to start with CNS with SciPy, but starting with the MNIST notebook is also totally fine. And unless you come in already knowing PyTorch, we would not recommend starting with the RNNs for text classification notebook. So, can I see a quick show of hands of like which category / notebook y'all would want to begin in? So, anyone who wants to start with the Intro to Python notebook? Okay, we have a few hands, and that's totally fine. This is gonna be like a really quick, like you can probably even finish in this session. And next session you will be able to start moving on to the neural networks MNIST. Who wants to start with the MNIST notebook, which is handwriting recognition? Okay, majority of people. That's great because this notebook is developed by Sparshear. It is pretty good. And who wants to start with CNNs with SciPy? Okay, we have less hands, but don't worry if you don't start from this one, because after you finish the neural networks with MNIST, you will move on to SciPy with the SciPy notebook. And are there anyone who wants to start with the RNN one? Perfect, because we are also trying to improve that notebook at the moment, so it's nice that no one's starting from that as their first notebook. So let's get into groups then. For the Intro to Python group, can we have y'all kind of gather over here? The left column here. And for the MS group, you can stay in the middle.
Why don't we wait until after you present about grading?
Let's do that. Okay. Yeah. For the MS people, let's gather in the middle. And for the SciPy people, let's gather on the right-hand side. All right? All right. So basically, the MS people are in the middle, the Intro Python people are in the left. Yeah.
No experience means like zero.
Like, are you comfortable with Intro Python?
Yeah. I've been going and stuff.
Oh, okay, then you're probably fine with starting with MS. Yeah. Wait, yeah.
Yeah, wait, what are the
Python and this type of
no RNN.
no RNN today. So yeah. Yeah, I'm gonna get
Alrighty.
Yeah. So yeah, we want some majority constants. And then like someone else. But if not. Okay, so the link to be able to get access to these notebooks is going to be here. So it's also written here in the cluster. So this bit.ly link right over here should bring you, like if I were to try to show you over here, should bring you to a little Excel spreadsheet, and on it you will be able to see everything related to workshop this quarter. So that's a weird browser I'm using. Okay, so like as you can see here, let me full screen this if I can. Yeah, as you can see here, we have the asset cluster is where you find everything related to workshops, right? For those of you who were in beginner track last quarter, you may recognize this. Those of you who aren't, this is where you can find everything. I'm also going to post a link to the asset cluster in the Discord channel, in the workshops channel in a little bit. So again, this is where you can find it. Yeah, ACM _AI _24 W _cluster. And on the left-hand side, you can find each of the notebooks. We recommend starting with a skeleton one. And then on the right-hand side, you'll be able to find recordings from theory track. So, and yeah, and one important thing is when you say click on a notebook, for example, make sure to make a copy before you edits, because I think you can't make any edits unless you make a copy, because we have set it to view only. So when you make a copy, just make a copy in your own drive, and you should be able to edit it however you want. The internet is not liking us today, but we will continue. So officers for the okay.
Just present the content.
Yeah. Okay. Oops. Okay, so today, the very short presentation for a workshop is to be on gradient descent, which is the question of how do machines actually learn, right? We talk about machine learning, and we talk about having these models, and we talk about all these things. But a lot of times we're asking the problem of how do we go from having a neural network model to actually the machine being able to find the best, say, weights and biases, the best parameters that will be able to achieve the task that we want. And the process, very broadly speaking, is called gradient descent. And to talk about gradient descent and optimizers, the first thing we need to talk about is process of optimization. So first of all, we have to be able to let a model improve and be able to solve a problem. We have to have some way of telling them, hey, or hey, you're doing great. We have to have some numerical way of quantifying how well the model is doing. And we do so via something called the loss function or the objective function or the residual. See a lot of different words to describe the same thing there. Specifically, what an optimizer does is it tries to lower a model's loss, aka how well the model is doing, by nudging the model's weights iteratively, right? The model has weights that determine its behavior, determines how it takes an input and kind of manipulates that inputs and gets us to an output. And that output loss can be something like, say, you're doing the task regression, right? You're trying to map if y'all remember from like linear regression, logistic regression, we were trying to a bunch of points, trying to fit a data point. The loss may be, the mean squared error of the points to the line, right? That's an example of a loss function. And what the optimizer does is, given something called a gradient, it tries to lower that model's loss by iteratively nudging our model weights or our model parameters. So then you're like, okay, that sounds fine, but how do we actually do this? To see how able to actually be able to nudge the model around and find some sort of minimum, what we have to look at is looking at the idea of model weights. So let's say we have a model with two weights, right? The weights be written as a vector, W equals to W1, W2. And in this case, the weights in the case for example, linear regression can be AX plus B, right? The A and B are our weights. They're what determines the behavior of the model. And our loss function will be some arbitrary function that takes in the outputs of our model and takes in the label or the ground truth or what we want the model to output. And it gives us a numerical, the lower the value, the better the model is performing. So sometimes we also call it the error. But the key thing is the loss function is something that is being affected by the model weights, because so we actually write it in terms of the model parameters. Specifically, imagine our two model parameters being in one on the x-axis, right, our W1, and one on the y-axis on W2. And we were to calculate the loss of the model, say, with all of our data, given that our W1, W2 is somewhere on the plane. So then you can imagine how if our z-axis is our loss function, we are creating a loss landscape where our goal is to find the minimum. I'm going to reiterate this again. What the loss landscape represents is this axis here represents all possible forms our model weights can take, right? All possible combinations of the values of W1, W2 that it can be in a 2D plane. And the kind of vertical axis represents the loss of that model if it had those weights. Say we pass in every single one of our data points, right? And you kind of imagine how then our goal is, can we find a minimum? Because if we found a minimum, that means we have found the combination of model weights, W1 and W2, such that our loss is minimized, aka our model is doing the best it possibly can. right? So that's the idea. And the key thing is this is not limited to 2D as well, because models can have billions of weights. Like, the text stable diffusion that we were just talking about, the text to image model has 1.4 billion weights. And large language models can often go up to hundreds of billions of weights. Yes. Right. So a weight is just anything that defines what a model is. So in the case of, again, like I'm going to use it, like let's say our model is a linear regression model where it's ax plus b, right? That's the formula it tries to that's the formula it represents. Then our a and b is what determines what this ax plus b looks like, right? How our model takes in an x and outputs a y, because y equals ax plus b, right? So in this case, a and b are our weights. So it is basically the parameters that define what a model is. And specifically, what we're going to be talking about next week, neural networks, these parameters are matrices, right? And that's what we're going to be working with. But the key thing is weights are what defines the behavior of a model. It tells us how the model will take in an input, manipulate that input to get to some sort of outputs. So that's what weights are. And weights typically can be represented as just a vector of a bunch of numbers, right? Because models are all mathematical objects. They're really just a bunch of floating point numbers that define its behavior. Does that make sense? Basically, we don't want to say they're constants because the process of training changes them, right? But yes, they're just numbers. They're a sequence of numbers, if you will. Exactly. We're slowly nudging the weights so that we're at a minimum of the loss landscape. Because where we are on the loss landscape depends on what the model weights are, right? So again, like, going back to the idea of having billions of weights and not limited to 2D, like we can imagine having this really high dimensional plane where like this, it represents what our model looks like. And our vertical axis is the loss landscape. We're trying to find a minimum. So the question becomes, how do we find a minimum? We do it via a process called gradient descent. Can I see a show of hands? Who here has heard the word gradients before? Good number of hands, right? From Math 32A, I'm supposing. Exactly. Can someone remind me what a gradient is, if you remember? Sorry? It's a slope, yes. And specifically, do you remember like the slightly more mathematical definition? It points in the direction of greatest change. And mathematically speaking, it is, it's going to sound a little bit more, a lot, but it is basically the partial derivative of our final loss value, which is, remember, it's a scalar, right? It's a single value with respect to every single one of our weights, right? So it is going to be the same shape as our weights, the same dimensionality as our weights, because we're doing this for every single entry in the weights, right? And that's all it is. It is the partial derivative of our loss function with respect to every single one of our weights. And what are y'all's names? Dhruv and, sorry? Sachin. As Dhruv and Sachin said here, it points in the direction of the greatest slope or the greatest ascent, right? What the gradient, where the gradient points at tells us, hey, here is the direction I should go so that my function is increased the most. In this case, our loss is increased the most. So for example, let's say we have this little projector. If say our model is at, and this represents our loss landscape. If our model is over here, where do you think the gradient would point? This way, right? The gradient will point this way because this is the direction of the greatest ascent. It tells us where we can go so our elevation increases the most, right? Like you can go this way, it also increases, but not as much as if we were to go this way. So that's what a gradient is. So it tells us where to go if we want to maximize our loss. So to minimize our loss, we simply go in the opposite direction. Hence, gradient descent, right? And so the process of gradient descent just becomes, we have our weights, say we pass in some amount of data, we're able to then say, we use that data to calculate our gradient. Again, you're like, how do we calculate our gradient? It's a little bit more complicated. It involves a lot of chain rule, but we're going to talk about that in both theory track next time. Next Monday, we're going to talk about it in a lot more detail on theory track. So definitely attend that if you want to know how that works. But essentially, we just pass in some data, we calculate a gradient, we nudge the model in the negative direction of that gradient. We pass in some more data, we calculate a new gradient because the model has changed its position now, right? Because remember, gradient is a strictly local thing. It depends on where your model is. And we nudge those weights in that direction a little bit more, and just keep doing that. And we may add a little constant in front of the gradient that we're nudging called the learning rates, because if and usually this learning rate is quite small because usually we're just passing in a small batch of data. So that's not a great approximation of what the whole gradient is. So we're almost being more conservative. So that's what gradient descent is. And that's how machines are able to, quote unquote, learn. Is that gonna make sense? Okay. For those of y'all who attended beginner track last time, this should be a bit of a review for you, but yeah. So yeah, again, we're just taking a walk down the lost landscape hill. You can kind of see this happening with this over here, where like this is the gradient, and the model is slowly stepping down. ACM Hack has a pretty cool simulation on gradient descent itself of like, we start from here and then the gradient keeps pointing us to these directions and we can get to a minimum like that. Then we can talk about something called a mini batch and stochastic gradient descent, which is where we actually involve our data. And we ask the question of, okay, but what are we using to calculate the gradient? Where is this idea of loss coming from? So the question is this. Every time when we calculate the gradients, every iteration, we have three choices. Either we can feed in all of our data, right? Sounds good, right? Because we feed in all of our data, we have the best approximation we have of what our loss would be, right? And the way you usually do it is basically you feed in all your data. It gives you outputs for every single one of your data points. You just calculate your loss for each data point, what it would be, and you just average it, right? The average loss across the entire data set. But the issue is, machine learning data sets can get really big really quickly. For example, for the NS people, you guys are going to be working with a training data set of 60,000 images. That's not going to fit on your computer's GPU, right? That's going to make your computer explode. So the other end of the extreme is, what if we just put in one data point at a time, right? That sounds efficient. We can get a gradient from it. But the issue with that is that's not very accurate. Because if we were to just pass in one data point at a time, what if we get an outlier in this, right? What if this image of a cat is particularly looks like an image of a dog, right? Then the gradient wouldn't be very accurate because we're using an image that's slightly outside of the data set. So the gradients that we calculate will be very sporadic. Therefore, the solution is to use a mini batch where we choose a very small subset, very small portion of the data set. We pass that in instead. Usually that portion is, say, 64 images, 128 images. That's a pretty decent batch size today for these models. And if we were to go to like the sort of large language model training side, they use like millions of tokens as a batch, but like it's and that's out of billions or even trillions of tokens of data. So like it's going to be a very small subset of data sets, and we're hoping that by selecting the small subset, it is a good enough approximation of what our gradient would be if we were to pass in the entire data set. Does that make sense? So that's what mini batch gradient descent is, right? Again, all data use GPU screen in agony. Some of the data is mini batch gradient descent. So we can have a batch size of 64. So a bit of a summary. So originally, when we say gradient descent, we mean using all the data. When we say stochastic gradient descent, which may be a term that you've heard of, we mean one data at a time. And mini batch gradient descent means a small batch of data at a time. But nowadays, no one really feeds in all data at a time or just feeds in one data point. When we say gradient descent, stochastic gradient descent, mini batch gradient descent, we're usually referring to the same thing. We're talking about the process of calculating gradients and doing that nudging process. And the amount of data we're feeding in each time to calculate the gradient every iteration is just going to be a small batch, a small subset of the data. So just for terminology's sake, whenever in the future we say just gradient descended, that's what we're referring to. Does that make sense? Yes. Right. So what the gradient signifies in the model is this is the directions I want to push the weights of the model such that, at least in this very local context, in the current state of the model, it will decrease the loss the most. And we don't want to do it too much because, again, it's a very local thing, right? Like, like the gradient here points upwards, but the gradient here points down, points in this direction, right? So it's very local. And because of that, we don't want to push it in that direction too much. That's why we have a learning rate. And learning rate is usually like 0.1, 0.001, something like that. Does that make sense to you guys? Yes. Yeah, like no one really trains with just one data point at a time nowadays. Like people only do it if your computer is now powerful enough, your models are absolutely huge. But like, you know, practically speaking, we always talk about some sort of batch size. Even you can say a batch size of 1. Well, we always talk about some sort of batch size. And when you're training your own model, say with MNIST, you're going to be deciding what you want your batch size to be. A smaller batch size will make your model run faster, but maybe less accurate. But also running faster means you can run for more iterations. So that's a little trade-off that you will be kind of playing around with and seeing which way your model will train better. A larger batch size means your gradings are better, but it's also slower to do so. Like if you have twice the batch size, that means the grading will take twice the amount of time you calculate, because you have twice the amount of data you're feeding. So, you know, that's a trade-off that you will be looking at and, you know, trying to figure out. Does that make sense? Okay, cool. I think that's all the that's all the things we're gonna be talking about today. So now with that in mind, feel free to download the notebook, and we're gonna have officers going around trying to help you with Intro to Python and you know, getting started with the notebooks. And in the future, this is basically going to be like a like a semester work session where we get to work on these notebooks. And you know, if you have any questions, we're all here. And we're also gonna be helping you throughout the process. Okay, so to make this a little bit easier, try to like get a little bit closer together if you can, especially with the MNIST group. But yeah, now we're gonna have officers going around trying to help you out with the notebooks.